All right, so we are back for the final section of nonlinear solvers, and today we are going to finish up the discussion on nonlinear equations. We'll do one last discussion about Newton's method for a single nonlinear equation, and then I will cover systems of nonlinear equations, that's two or more nonlinear equations coupled together, and see how we circle back to linear systems of equations, which we covered early on in the semester. These linear systems are literally everywhere. Now, the discussion on nonlinear systems is going to be brief or a little bit quick, because now we know what the deal is with a nonlinear equation. But those slides should serve as a reference for you for the future. They do serve as a reference for me as well. Now, before we head towards systems of nonlinear equations, I want to discuss with you a little issue with Newton's method. Now, recall Newton's method. What it did, you start with an initial guess, and then at that initial guess, you essentially draw a line, okay, whose slope is tangent to the curve at that point. Okay, so that's the f prime, that's the derivative. So essentially, you draw that line and intersect it with the x-axis. The intersection with the x-axis, that gives you the new guess for the new root. Now you draw the vertical line and then take another straight line, and so on and so forth. Now I'm going to give you this curve over here. Okay, this is one of the curves we discussed. Actually, we're finding the root, this root over here. Okay, now I want you to consider what would happen visually. Okay, graphically, think about it. If you were to start with an initial guess at -2, so over here, your initial guess is over here. So you're gonna take the function value f at -2 and then draw a tangent, a line that's tangent to that curve, and intersect it with the x-axis. Okay, and that is going to be your new guess for the root. So tell me visually what will happen if you start with an initial guess at -2. Okay, show visually that what's going to happen is that the Newton's method is just going to get stuck in this local minimum over here. Now this curve doesn't intersect the x-axis over here. This residual function does not intersect, so there's no root over here. But I want you to visually think about what happens with Newton's method when you choose an initial guess inside a local minimum. What's going to happen to the method? All right, take a moment and I will finish off the discussion on Zoom. So I'm now back on Zoom. I apologize about, again, the earphones. I hope you heard me okay on YouTube. YouTube, as my kid calls it. All right. So what do you think about this? What's going to happen if we choose a x equal -2 initial guess? No need to do any calculations. Just think about it visually. So Newton's method, essentially what it does, it draws a straight line that is tangent at, at the curve where your initial guess is. Okay, so we start at -2, and then we draw a line at f of -2. Okay, and then we intersect with the x-axis, get the new initial guess, and keep repeating. What do you think is going to happen?
I'll take a stab at it.
Yeah.
Yeah, so the tangent line, so the next approximation, the tangent line is just going to be completely flat. It's never going to cross the x-axis again.
Okay, maybe completely flat. And then, yeah, if it hits that, if it hits a parallel to the x-axis, if it hits the local minimum, that's it. It will diverge. There's no, it's going to intersect at infinity. There's no solution, right? But, if it's a little bit off, it's just going to keep oscillating back and forth in that local minimum, right? There's no way for it to get out of that local minimum, okay? And that's a problem with Newton's method. If your initial guess is bad or is not close to the actual root, you're done. Okay, I'm going to show you an example. I put together a little GUI.
Professor, real quick question. What would happen if the local minimum is our root? If we had that local minimum be the only, or be one of the only 0 points? Okay, thank you.
All right, now that we've seen one of the caveats of Newton's method, you got to be careful how you choose your initial guess. For simple functions like this, just plot the function, pick your guess close to where the function intersects the x-axis, and you'll be good to go. For complex systems where you cannot visualize, where there's no way to visualize actually, typically there's guidance from the physics, and that guidance is going to help you pick your initial guess, and if you're lucky enough, you're going to be okay. Now, there are other advanced techniques to help out with these situations, but they all are based on variations of Newton's method and the bisection method and what we covered. All right, our next story in this chapter, and we will finish off this chapter, are systems of nonlinear equations. So when we took a single nonlinear equation, it had a single unknown variable, we called that x. We were able to plot that. We took the residual function and we found the root. Now what does it mean now when you have two equations that are coupled to each other, but they are nonlinear? Okay, what does it mean to say that to solve the system? So take these two equations, for example. 1/2 x cubed plus y equal 4x and y equals sine x e to the x. Clearly, they are coupled to each other. You can probably take y and substitute it up there, but suppose you're not going to substitute that up there. What if you had like log y equal, sine x, or something that you cannot untangle? Okay, let's say you're just keeping those two equations the same because we want to do a general way of doing nonlinear systems. What does it mean to solve a system of nonlinear equations? It specifically means that just like a single equation where we said it's going to intersect, when we write it in residual form, it's going to intersect the x-axis or the y equals 0 axis. Okay, the same thing applies here. Solving a system of equations is finding those points where the equations intersect with each other. Now, we were lucky enough here because this is a system with two unknowns only, so I was able to plot y versus x, okay, and then see the intersection. But once you write this in residual form, it's the story still holds. It's where those curves intersect each other, but specifically when they intersect, the x-axis equals 0. But in general, when you're solving systems of equations, and this applies for linear systems of equations as well, it's finding all of those points where all the lines intersect each other, all the curves intersect with each other. Now we're going to take Newton's method and apply it for systems of equations. Okay, I'm going to guide you through this one step at a time, and we're going to try to do it together. Okay, now just like we did last time with a single equation, I want you to take a moment and write those two equations in residual form. Okay, I'll wait here on YouTube because we're running out of time, but I want you to try to just write those in residual form. Remember the residual form, rather than intersecting with some arbitrary curve or arbitrary value, we just want to intersect everything with the y equals 0. So in other words, move everything to one side, and that gives you your residual function. However, here we have two residual functions, okay, because we have two equations, all right? So go ahead and try, call those residual functions R1, R2, or F1, F2. We've been adopting the F nomenclature, so just do F1, F2. just move everything to the left-hand side, and that gives you the residual functions. Okay, I'm going to give you the answer here. All right, so the residual form is just simply take everything on the left-hand side and call that a new function. So f1, we took 4x to the other side, and f2, we took sine x, ex to the other side. That gave us the two residual functions. Now be consistent in how you define your residual functions. It's not going to be a problem, but I would be consistent. I always move everything to the left-hand side. Okay. Now solving this system of equations means finding x and y, or the unknowns, such that both f1 and f2 are equal to 0, rather than then intersecting each other at kind of arbitrary y values. Okay. Now the next step in Newton's method, remember, was to write the Taylor series of the residual function, right? Now in this case we have a multidimensional residual function. We have multiple multidimensional residual functions, right? Because f1 has both x and y in it, and f2 has both x and y in it. Now the Taylor series for a single function, we know it's like f at x0 plus f prime, plus 1 over 2 factorial f double prime times delta x, and so on and so forth. Okay, the same thing can apply to multi-dimensions. It gets really complicated, but luckily we are only interested in the first few terms, or in the constant plus the straight line terms in the Taylor series, so we don't need the high order terms. So what I'm going to do, I'm just going to write those first few terms in the Taylor series. For a function that has two variables over here, we start with the evaluation of the function at some initial point around x0, y0. Now remember, we're going to use this as our initial guess for the roots. Okay, now we have two roots, x and y, so two values for the root, right? So in other words, it's the x and the y value, okay? But that is the evaluation of the function, the residual function, each one of those, at x0, y0. And then simply you have these two linear terms, x minus x0, derivative of f with respect to x, and then y minus y0, derivative of f with respect to y, okay? Evaluated at x0, y0, and evaluated at x0, y0. So there's a typo here. Those two derivatives are missing, that they need to be evaluated at x0 and y0, okay? So now that's the recipe for a Taylor series for a function of two variables, okay? Now I want you to take this and write it for a system, just apply this formula, write it for a system of equations described by two residual functions, f1 of xy, f2 of xy. You don't have to specify what f1 and f2 are, just plug in just change the values over here. So this would be f1, 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 and then f2, f2, and f2. Okay, go ahead, take a moment just to do this. I know we're supposed to do this on Zoom, but I need to rush this a little bit so that we can finish off ODEs by the end of the semester, okay? So now we're just applying the Taylor series like we did previously. We had only one residual function, now we have more than one. I want you to try it out for two residual functions with two unknowns, okay, x and y. So just write out this Taylor series. This is just an exercise in you writing out what you're seeing here, okay? If you don't write it out, it's not going to stick in your brain. There's a critical typo over here in that this df dx and df by dy, those should be evaluated at x0, y0. That's the point around which we are expanding the residual function. Okay, again, remember Newton's method, we are after a recipe to improve our initial guess, and we're going to take that recipe from the Taylor series. When we were dealing with a single equation, it was easy, that Taylor series. Now we have two Taylor series, we need to figure out how we combine them together, okay? Just substitute nomenclature. All right, I'm going to give you the answer over here. for the first residual function, the Taylor series for the first residual function is simply f1 at x0, y0 plus x minus x0 partial f1 with respect to x evaluated at x0, y0 plus y minus y0 partial f1 with respect to y evaluated at x0, y0. I don't care about the higher order terms because we're going to truncate those. That was the essence of Newton's method. Same thing for f2. You're just simply substituting, putting in, instead of f1, you put f2, but they're all evaluated at x0, y0, and notice the differences here. Now this difference, we're going to use this formula to essentially improve our guess x0 and y0, but we now have more than one equation, okay? So what do we do next? Recall with Newton's method, we were given a residual function, we wrote the full Taylor series of the residual function, and that we truncated all the high order terms, okay, all of those terms over here, because we wanted to solve for x. So essentially we approximated the function with a straight line, okay, this is our approximation, and then we said, okay, set f of x equal to 0, that's the residual function, so put 0 over here, and then solve for x, because we know f at x0, we know x0, we know f of x0, and that gave us the recipe for Newton's method. Okay, gave us the recipe for improving the guess. So we started with x0. The recipe to improve x0 is in this x, and then we repeat. We repeat over and over again. Now let's do the same for these two residual functions. Then do the same also for more. We'll do that at the end. But now starting with these two, all I need are those initial terms. Now why do I leave off the higher order terms? Because they have x squared and y squared in them. It's not easy to solve for x and y in that case, because then you get a quadratic, and which root do you pick? It becomes a multiple root problem, you know, it becomes really ambiguous, let's say. Okay, so that's why we only pick these linear terms, because from those linear terms we can extract x and y. So let's see how we do it for 2D. So we're going to apply the same strategy. We knock out the high order terms, so we are left only with this. These are an approximation now, okay? So an approximation, all right? So now I want you to do the following. I want you to derive the Newton's method for multi-dimensional, for more than one equation. Like we did with the single equation, we set the residual function to 0. We are remember, we are after x and y, okay, that make the function, we are after the root, we are after x and y that make the residual functions equal to 0. So let's go ahead and set the residual functions to 0, okay, it's only an approximation, and then solve for x and y, okay. So when you do that, you get the first equation is just this guy, and the second equation is that guy, all right. So now when you look at this, when we had a single equation, it was just easy to extract x. But over here we have two equations, but how many unknowns do we have? f1, x0, y0 is known, because we know f1, we know x0, we know y0. X is not known, that's unknown number 1. x0, df1, dx, x0, y0 are known. Y is not known, that's the second unknown. But y0 and this guy are known, okay? So we have two unknowns, and we have two equations. So that system is closed. And now guess what? The unknowns show up in a linear fashion. So this is really a system of linear equations. And we're going to solve that system of linear equations now and get the roots, all right? So now I want you to write this and to think about writing this in matrix form. Whenever you have a system of linear equations, first thing you do is write things in matrix form. So that's our first two terms over here, f1 and f2. I put them in this vector, okay? Now, for x minus x0 and y minus y0, you see they're showing up. The matrix is right in front of you. It's a 2 by 2 matrix in this case, right? And the coefficients in the matrix are the partial derivatives of f1 with respect to x, and partial derivative of f2 with respect to x, partial derivative of f1 with respect to y, derivative of f2 with respect to y at x0, y0, all evaluated. And then you have this solution vector equal to 0. Now, this is known, and this is known. This guy has the unknowns in it, x and y, and we know x0 and y0 what they are, because those are the initial guess. So now we're gonna name things so that if you're not convinced that this represents is identical to this system of equations, just carry out the matrix vector multiplication. For the first equation, you get f1 plus partial f1 by partial x times x minus x0, so that's this term, plus df1 by dy times y minus y0, that's this term, equal to 0. Okay? So if you're not convinced, carry out the matrix vector multiplication. Okay, now if we call x0, y0, the double, the point, okay, if we call that a vector x sub 0, okay, that's a vector, and if we also call f1 and f2 a vector f, okay, then this guy can be written as vector f evaluated at x0. Now this matrix is a special matrix that we're going to discuss a little bit later. It's called the Jacobian. Okay, it's a very special matrix that applies to all systems of equations. It's called the Jacobian. We're going to call this J evaluated also at x0. Now remember, x0 in this case is a vector of points, x0 and y0. And finally, what I'm going to call this, I'm going to call this delta, because this vector over here includes the distance between the existing guess, x0, and the improved guess. That's delta, right? That's the distance between the new guess and the old guess. Remember, x and y are the new guesses. So instead of solving for x and y, we're just solving for the distance. If you know x0 and y0, you can pull out x and y very easily, okay? But this is how we write Newton's method for systems of nonlinear equations. And then once you have this nomenclature, all you have to say is f at x0 plus j, Jacobian at x0 times delta equals 0. And that's a system of linear equations. And the solution is simply, you take f to the right-hand side, and then you apply the inverse. Because our goal is to solve for delta, right? So we multiply by the inverse of the matrix, you get delta, that's the distance between the previous guess and the new guess, and the improved guess, is equal to the minus inverse Jacobian times f. Now, we know what these are. We know f is just simply the vector of your residual functions, f1, f2, could be f3, f4, or f however many, 3 million, 3.5 million, okay? Residual functions, doesn't matter, it's just a vector. The Jacobian is a special matrix, we will discuss that in a second, but it contains all the partial derivatives of all the residual functions differentiated with respect to all of the independent variables. So you notice we have derivatives of f1 and f2 with respect to x and y. Okay, so if you had a system that had x, y, z and 3 residual functions, f1, f2, f3, that Jacobian is going to contain partial derivatives of f1, f2, f3 with respect to x, with respect to y, and with respect to z. It covers all of the derivatives. And that's understandable because in multi-dimensions, you need to figure out what plane or what curve, what multi-dimensional plane you are at to be able to get to the improved guess. Now when you write it in this form, it simplifies everything. Because now this form is no different than the algebraic form for a single equation. Think of the following. Delta is the distance between x and x0. So if you were to take x0 to this side for the one-dimensional Newton's method, you get delta over here is minus 1 over f prime times f of x0. F of x0 is simply f of x0, but minus 1 over f prime is simply the inverse of f prime, right? However, for multi-dimensions, that inverse of the derivative is described by the inverse of the Jacobian. Because in 1D you only have one derivative, but in 2D you're going to have multiple derivatives. In 3D you're going to have many, many more derivatives, right? So it's just simply a generalization of Newton's method for 1D when you have multiple equations you're dealing with. Now, because the way I presented this so far, we had x0 and x, right? But we know we're going to keep iterating because you start with x0, you update, you solve for delta, you update your root, you use that as your new guess, right? And then you improve over and over again. So, excuse me, the best way to write this is with a counter. So if you are at iteration k, you are solving this system of equations, j at x evaluated at xk minus f of xk, and delta is simply the distance between the new root xk plus 1 minus xk. So when you solve for delta, then you can pull out xk plus 1. And you converge really when delta is less than a certain tolerance. Okay? The algorithm is pretty simple. We'll show you how we apply it to a general case, but just for this case where you have two unknowns and two equations, you are given f of x, you know the residual functions, you know your initial guesses, x0, and you can compute your Jacobian. Because if you know the residuals, you can do the derivatives, or you can do them numerically as well, right? Because we know how to do finite difference derivatives, okay? Then the first step, you calculate your Jacobian and your residual function at that initial guess that you started with. Then you solve for delta, you update the roots, so x1 and y1, right? And then you check for convergence. If you're not converged, you use those as your new guess, and you repeat, and you repeat, and you repeat. Now, how do you solve for delta? We're just simply doing the inverse, okay, over here, because we're dealing with simple systems of equations in our case. But in my research, for example, the example I just quoted you, our Jacobian is very, very sparse. It's very sparse. So out of those 3.5 million, there's probably only 100,000 non-zeros, okay? And that's a very sparse matrix. What we do to solve this, we use an iterative solver, okay? So it doesn't matter how you solve this system. You know, if your Jacobian is tridiagonal, you can use the Thomas algorithm. Who cares, okay? As long as you solve it, all right? Okay, let me show you an example. Well, this is the example we started with, right? This is f1 for half x cubed plus y minus 4x, and this is f2. First step is you calculate your Jacobian analytically, and simply just fill in the blanks over here. You take the derivative of f1 with respect to x, f1 with respect to y, and so on. Now, you do it analytically in general, because at this point you don't know what x0 and y0 are, okay? Once you know them, you just simply substitute in this matrix, you evaluate the matrix, you solve a system of equations, and repeat, okay? So here's an example. If we were to start with an initial guess -2 and -4, I encourage you to do this by hand at home. In the exam, I might ask you to do just 1 or 2 iterations, just to see that you can evaluate the Jacobian correctly, okay? Calculate the Jacobian. Now, we did the formula for the Jacobian. We simply now have to apply the Jacobian, J, at these initial guesses. And that Jacobian turns out to be 2, 1, and then -3, 1. It turns out that this Jacobian over here only has x in it, okay? It doesn't have y, so it doesn't matter, whatever. We don't have y in it, that's fine, easier. For your residual functions, those are just simply f1 and f2, okay? You just simply substitute the x and y values, okay? You just substitute the x and y values, and you get f0 and 2.7. Interestingly, f equals 0, that's actually going to be a root for, well, it's not going to be a root for the system, right? Because we need both of those functions to be 0. But interestingly, this residual function on its own is equal to 0 in that case. Okay? And then you solve for delta. So essentially take the inverse of the Jacobian, multiply by f, and negate, and you get delta. Then from delta, you extract the actual root, and then you reuse those roots again over here, and then repeat, and then repeat, and then you can continue repeating until you converge. Okay? So this was done by hand, and it's just a simple, annoying calculation, okay? But we want to do that in Python, clearly, and you can do that easily in Python. I'll show you in a minute how to do it. Some tips when you're dealing with nonlinear systems is before you go to the computer, just formulate the problem by hand, define what your residual functions are, the vector of residual functions. Once you stick to an order of equations, you have to respect that order, f1, f2, f3. Don't change the order, don't change the signs, just stick with that, okay? Keep that, carry that along in your entire derivation. Define what tolerance you want to use, what the initial guesses are. In most cases, you're not going to be able to plot things, okay? When you have 3 or 4 or 10 equations, there's no way you can plot. You gotta have to figure out an initial guess, and then carry out a few iterations if you can. If the system is simple enough, like this one, 2 by 2, then go ahead and do a couple of iterations. When you implement in Python, you need a couple of functions in addition to your Newton routine. Just like in the 1D case, we defined one residual function that returns f of x, or the residual at x. In this case, you want to return a vector of residual functions. And that a vector of residual functions is going to be applied at the vector of initial guesses, or the vector of your current iterate, or your previous iteration xk. Remember, you had f at xk. But in this case here, you also have to define the Jacobian. In the 1D case, the Jacobian was simply a single derivative, okay? And we did that either analytically or numerically. Over here, your Jacobian is going to be a matrix, okay? And that matrix, remember, it needs to be evaluated at the current, or at the xk iteration, at the previous iteration, okay? xk or x0, think of it as the current initial guess if you want, okay? But use the word iteration. At the kth iteration, we're predicting k plus 1, okay? Use the kth iteration. And finally, you write your Newton solver as a function. And it should have the following arguments. It should take the vector of residual functions, it should take the Jacobian, it should take the initial guesses, and it requires a tolerance and potentially a maximum number of iterations. Okay, here's an example of how you would implement this for this system of equations. This is easily extendable to any case you want. So I'm just giving you this as an example for this case. So this is my Jacobian function. I'm going to assume xval is a vector of iterates. Remember, when we call this function, we're going to give it this x0 and y0, and it's going to take it and apply it in the matrix. So what I do first is take out x and y by calling, the xval0 and xval1. That gives me the first entry in the xval array and the second entry in the xval array. And I return a matrix. This is my Jacobian matrix. Okay. Now look at that. It looks identical to this guy, right? 1.5 x squared minus 4. That's the first entry in the matrix, and then 1, and then cosine x e to the minus x, etc., and then 1. Okay. And those x and y values, they are actually these guys. Okay, x and y. You might call them x0, x1, or whatever, z and w, whatever you want, doesn't matter. It's just going to return an array with numerical values in it. Okay. Now for my residual functions, the vector of residual functions, this guy, f1 and f2, evaluated at x0, y0, or the kth iteration. Again, I pass the kth iteration to the function evaluation, so f at xval, and then I pull out x and y, okay, just like I'm doing over here. And then simply f1, I evaluate the first residual function, second residual function at those values that came into the function, okay? And then I return them as a vector, f1 and f2. You have to respect the order. If you swap the order, it's going to mess everything up, because then your Jacobian is not going to be consistent with how you ordered your residual functions, okay? Here's another example where it's an intersection between a curve and an ellipse. Those are the roots over here, and these are the equations. You write those in residual form. You get the Jacobian matrix, and it's just simple routine exercise to do by hand. Now, the more realistic case is when you have many equations, 10 billion equations. The example I quoted you was one of the smallest examples we were dealing with, solving fluid mechanics problems. On a small 32 by 32 two-dimensional problem, we ended up with about 3.5 million equations. So you could have these residual functions could be huge, very large number of residual functions, okay? We just simply call them the vector f. Now, how you implement this vector f, that's where you're gonna earn your money. How you implement this, how you automate it, for example, because clearly you're not gonna hard code this one equation at a time. Luckily, all of those equations in practice, when you have a large system of equations, they have a template to them. So you do a loop and you fill in this entire matrix. Now, what's interesting here is the Jacobian, what the Jacobian is gonna look like, okay? We're gonna spend a minute discussing the Jacobian on the next slide. But the algorithm is the same. You just simply need to solve for the delta, which is the distance between the new iteration and the new guess, the improved guess, and the current guess. using this system of equations. J at xk equal jxk delta equal minus f at xk. And f is again this vector of residual functions. J is your Jacobian matrix. Now pay close attention to the Jacobian matrix, okay? For a system of n residual functions and n unknowns, okay? 4 residual functions, 4 unknowns, 15 residual functions, 15 unknowns. The Jacobian matrix always has the same structure. If you go column-wise, you differentiate with respect to the first unknown, okay? Now, pay attention here, x1 and x2 and xn, they're not the iteration count. They are unknown 1, unknown 2, unknown 3, unknown 4. Don't confuse that with the iteration index, okay? Remember, f1 is a function of x1, x2, x3, x4, whatever. f2 is a function of x1, x2, x3, and so on and so forth, okay? So if you go column-wise, you can do the think of the Jacobian in both of these ways. If you go column-wise, you are in the first column, you differentiate all of your residual functions with respect to the first unknown. So you see df1 by dx1, df2 by dx1, df3 by dx1, all the way to dfn by dx1. The second column contains, again, your derivatives of all the functions, but with respect to the second unknown, x2. So df1 by dx2, df2 by dx2, dfn by dx2, and so on. So the direction, column-wise direction, is you're changing the variable, the unknown, okay? You're changing the independent variable, differentiate with respect to independent variable. Now, if you read the Jacobian row-wise, it's the opposite, okay? The first row contains derivatives of the first residual function with respect to all the independent variables, okay? The second row contains the derivative of the second residual function with respect to all the variables, and so on. The nth row contains the derivatives of the nth residual function with respect to all the variables. I like to do it row-wise because I like to think residual function and then independent variable. Some people like to think independent variable and then residual, so they read it column-wise, okay? But you should be able to reproduce any kind of Jacobian just by looking at that. Jacobian matrix is a very special matrix, and it applies to essentially any system of equations. They could be linear, okay? So if someone gives you a system of equations, they tell you what's the Jacobian, this is the structure of the Jacobian. In essence, intuitively, the Jacobian essentially summarizes all the slopes at a given set of points. So remember, all of those derivatives are going to be evaluated at the previous iteration or the previous guess. So they describe something. Specifically, they describe the tangents, okay, in all the different directions with this multi-dimensional system of equations, okay? One other little hint is that, in general, to do this Jacobian analytically can be complicated. For our problem in my research, we do it analytically because it's a very sparse Jacobian. So we have to know where we have zeros and where we do not have zeros. But as an alternative, you can do a numerical Jacobian just like we did in the one-dimensional case. And you simply have to apply the finite difference formula with respect to the appropriate direction that you're dealing with. So let me switch back here. So for this derivative, you essentially fix all the other variables, x2, x3, x4, etc., and you simply take the finite difference, f1 at x1 plus delta x, minus minus f1 at x1, okay, and all the other variables fixed over a specific spacing of your choosing, okay? I'm showing it here in index notation. This is where index notation becomes very powerful. But there are tricks to do this in Python in one shot. I'm not gonna cover those because those could take us half an hour just to discuss them. We used to cover them in the past, but I found that they are not very useful. Typically, many of you, as you hit your latter classes, I see an email from you, hey, Professor Saad, I'm solving this system of nonlinear equations. Can you remind me or give me the code how to do that? And we just spend a minute on doing that. Now, all of this, all what I discussed, the great thing is you can use it with fsolve. So with fsolve, which is the built-in SciPy nonlinear solver, with fsolve, previously we gave it one residual function, one single valued residual function, and a single initial guess, correct? All you have to do to solve a system of nonlinear equations is simply give it a vector of residual functions and a vector of initial guesses, and it's going to find the root for you. Okay? And with that, I will end the discussion on nonlinear solvers. And I'm going to switch back to Zoom, have a quick discussion, and then we'll switch to our final and very important chapter on ordinary differential equations. All right, I am here. That was a handful. Nonlinear systems of equations can be pretty daunting. Trust me, every time I am dealing with those, I have to review my slides because there's a lot to think about, but once you write it in this vector matrix form, it simplifies things, okay? Your homework is not gonna include systems of equations, okay? So we're just gonna be dealing with a single equation because I think you can handle it, but you know, we need to spend a little bit more time to practice it. So I'm gonna tone it down a little bit on your homework and the exam, but you still need to understand the Jacobian, please. You still need to understand what we did, how we took the procedure of taking two equations or 10 equations and how we wrote the Taylor series to linearize them, and how we converted a nonlinear system of equations into a linear system of equations that needs to be, we're gonna do iterations on it over and over again to improve our guess, okay? I'll leave the floor open for you for some questions. And as I prep for my other slides, okay, let me see. And we will get started on one of my favorite subjects in numerical methods, which is, and in general, which is ordinary differential equations. And my promise to you is, so who's taken ordinary differential equations? Who has taken it? Who is taking it concurrently? Okay. Okay, did you understand, what did you understand about ODEs, or what did you not understand about ODEs? I'm not trying to pick on anyone. I'm just, you know, thinking about how I myself did not learn ODEs appropriately. It wasn't until later, you know, in my life where I'm like, you know, I had an aha moment, right? Because we tend to teach mechanistically. So what did you think about your knowledge of ODEs? Like, what's an ODE? Why do we need ODEs? What's so ordinary or extraordinary about ordinary differential equations? And why are they used? What are they used for? And why are they important? Nothing? That puts a lot of pressure on me now. Okay, so my goal in the next chapter, and at the expense of doing partial differential equations, which I think are too much for this class, my goal for this next chapter is to revisit the idea of ordinary differential equations, what they are. I'm not going to discuss how to solve them analytically. That's where the math course comes in. But I'm going to discuss with you how to think about ordinary differential equations and why they are useful. So we will start with an example of trying to derive an equation together, and then I'm going to ask you a question and ask you to derive an equation. You're going to be like, I have no idea how to derive this equation. And then we'll introduce the idea of rates of change and see how powerful that idea is. Then we're going to take a detour, discuss some definitions, a bunch of numerical methods, and then we get to systems of differential equations where it gets really, really fun. And together we are going to derive a model for the spread of a pandemic, specifically, and we'll apply it to COVID-19 with some numbers. And then we're going to develop a model with social distancing and see, you know, is it effective? Is it not? Can we, should we do 100%, shutdown, or could we do it with 50% shutdown, or could we do like shutdown, turn on, shutdown, open up again, shutdown, open up again, and see what happens with these different models, okay? But until we get there, we're gonna have to start slowly together, okay? So I'll see you on YouTube, and we'll get started with differential equations, okay? This is a very exciting topic in this course, regression and ODEs are my favorite subjects, okay? And I hope that excitement bleeds through, okay? I'll see you on YouTube. Oops. All right. Ordinary differential equations, numerical methods for ordinary differential equations. But first, we're going to talk about ODEs to challenge your current understanding of ordinary differential equations and potentially reboot it or complement it. Okay, you might, have learned half of the story. You might be missing just one little nudge in your intuitive understanding. I really stress on intuitive understanding of things because I don't like to memorize. I like to derive on the spot rather than having to. The only thing I want to memorize is just like multiplication table, right? But other than that, I don't want to memorize anything. I want to be able to derive it off the spot. Okay, there are too many birthdays in my life that I need to remember, so I need to leave some disk space in my head for those. Okay, learning objectives. Just to set you up to see what you're up against. At the end of this chapter, I hope that you'll be able to do the following. Define what a differential equation is, ordinary or extraordinary or partial. Define and identify dependent and independent variables, coefficients, the right-hand side of a differential equation. Distinguish between a partial differential equation and an ordinary one. Identify and classify ODEs. So is this ODE first order? Is it initial value, boundary value? Is it second order, linear, nonlinear? Identify initial and boundary value ODEs. I just said that. Describe the meaning of terms in an ODE. So a derivative, an advection term, a diffusion term. We're going to talk about those a little bit. A growth term, a source term. Create Python code to solve a single or a system of ODEs. We're gonna try to do this on our own, but then we're gonna use ODE int as provided in Python, so that we don't have to worry about just writing our own solver routines. And use explicit and implicit finite difference method to find a numerical solution for initial value ODEs for a single and system of equations, and use also finite difference to calculate the solution for a boundary value ordinary differential equation, and identify when the right-hand side is linear and is nonlinear. And this is where nonlinear solvers come in, and this is where linear solvers eventually come in. This is kind of like at the extreme end of ordinary differential equations. And calculate a numerical solution for an implicit method with a nonlinear right-hand side using Newton's method. This is like the most, we're like throwing everything into the pot. It gets really, really complex there. But if you do it systematically, all you end up with is a linear system of equations that you have to solve. Okay? And before we get started, I want to ask you a question. What is a differential equation in general? Just a differential equation. What is it? What do you understand? What if, your friend, your grandma, your family, someone sitting at the table, hey, what's a differential equation? I heard this term discussed on the National Geographic, and you are an engineer. Tell me, what's a differential equation? What would you say? What would you tell them? All right, let's talk over Zoom. While you take a minute to... Okay. And my question to you was, if your grandma, your kid, asks you, what is a differential equation? What will you say?
It relates one or more functions and their derivatives.
What if it's just one function? and its derivatives. The equation has the function and its derivatives.
Yeah.
Okay, what's the purpose?
To show a relationship either between different functions or the relationship of the single function and its rate of change. Yeah, just different physical quantities.
Okay. What else? Really, if someone stops you and asks you, you know,
I guess I would say a differential equation. I always thought of it as just an equation that relates the change of the original equation over time.
okay, yeah, there's a change involved, okay, and one of the questions that I'm going to challenge you with is, why do we need a change? Why don't we just say, here's a value, here's an equation for the value? Why do we need an equation for the change? That's the key challenge, right? That's gonna be the key challenge. Okay, let me switch to YouTube and give you my take on it, okay? All right, so your answers were not incorrect, okay? But we're gonna work together now on coming up with a answer that is satisfactory. I know internally you're like, yeah, that's the definition of a differential equation, but it doesn't really explain what a differential equation is. It's like the difference between facts and wisdom. Facts are just, data that are facts. There's this saying that says, facts tell you where you are on a map, but wisdom tells you where to go next, right? So what we just said are definitions. There is just a fact, but it doesn't tell us what to do with those, and what the power of differential equations are. Okay, so I'm going to give you the definition now, and then we're going to start tearing out that definition apart and understand why it's important. A differential equation, just like your colleague said, is just simply an equation with terms that involve derivatives. Now I want to start changing the words here. Instead of derivative, I want to use rate of change. Why? Because rate of change is an easier concept to understand, right? It's how fast you are changing something, or as you're moving, what is your speed? It's your rate of change of motion. It's more intuitive to think in terms of rate of change. So it's just simply an equation. It has a left-hand side, right-hand side, that involve rates of change of an unknown quantity. That's our unknown value. That's still a definition. It's still not satisfactory to me, okay? But we're gonna improve on that a little bit. Okay, here's an example of a differential equation. K d2t by dx squared plus u dt by dx equals 0. Typically, what's inside the derivatives are the dependent variables. In this case, it's t. This is actually an equation for temperature, how temperature changes. What's being differentiated against are the independent variables, and in this case, we only have one, which we call x. We call that the independent variable. K and u are coefficients in the differential equation, and they can be constant. They can be functions of t and x. Or other quantities, they're just coefficients. This is just nomenclature. But this is an equation that relates the second derivative of temperature, the second rate of change of temperature, and the first rate of change, okay? Now, why we need that equation is still a mystery to us. Why do we need this? Why can't we take a formula for the temperature, okay? Now, that's the key question to me, and that's why I think many miss in our education system. We miss giving out this information. So why do we need to develop equations with rates of change in them? I'll give you the answer and then actually do an example together so that it gets fixed in your head. In practice, it is easier to describe natural laws and complex systems by simply finding relations between the rate of change of things rather than the actual quantities themselves. So for example, you're filling a bucket in water and there is water leaking out of that bucket. You would say, or actually a month ago, our water main burst. How many people has that happened to? In my entire life in the US, You know, it just happened to me. And so the way the water company quoted this for me, oh, you were leaking 1,000 gallons per hour. It's a rate of change. So now I can understand, however, how much water I'm leaking and how much water I'm using, okay, per hour. I can then relate those two to how much water I'm using in total, okay? And that rate of change, rather than them telling me, oh, you consumed 12,000 gallons yesterday. What is that 12,000 gallons? Does that mean 500 gallons per hour, or, you know, is it fluctuating over time? I don't know if they gave me just a number, but telling me you're losing 1,000 gallons per hour, or you're losing 1,000 gallons per hour in the morning and then 2,000 gallons at noon, and then, you know, the rate of change is a little bit more descriptive. Now, I'm going to actually guide you through an example specifically to show you that it's easier to deal with rates of change rather than quantities themselves. Okay, let's do this example together. Now consider the following example, and I think the best way to teach ordinary differential equations is through population growth models, because those are very intuitive to understand. So to do this, we're going to consider a population of a unicellular organisms called paramecium. These organisms, they just keep splitting in half, just very basic cellular division. Okay, in this population, the individuals divide once per day. So each individual, you know, once in every 24 hours, they split into two. Okay, so starting with a single individual at day 0, we expect in successive days to have 2, 4, 8, 16, 64, etc. individuals over in the population. So the x-axis here is the number of days, starting from, you know, day 0, day 1, day 2, day 3, and so on. Okay, so starting with P0, that's our initial population. Could be more than one, but in this case, let's just take one individual. After 1 day, sorry, we have 2 times this initial population, right? Because this one cell turned into 2, so now we have 2. If those were 2 cells, we would have 4 over here, right? So P0 is the initial population. P1 is twice that initial population. P2, after 2 days, right, you have now 4, you doubled, okay? So now I'm asking you, what is the population of paramecia, PT, after T days have passed? Okay, so after 1 day you had 2P0, after 2 days you had 4P0, okay? So after T days, find me an equation for this population, okay? Take a minute. It's just a simple recursion formula. Do it for, you know, 3 days, 4 days if you want, and then just generalize to T days, okay? Trust me, there is reasoning behind all of this madness and why I'm taking you through all of these examples. This is just to show you, so I'm going to keep moving on with you with this example until we hit a point where you cannot derive a formula. And then you'll realize it's easier to derive something else. So let's see, come up with a formula for the population after T days have passed. If you're starting with a population P0, could be one individual, could be 10, one cell, or 10 cells initially. After 1 day, you double. After 2 days, times 4, and so on. Any takers?
Can I try? So PT equals 2 to the power T P naught.
Yes, that's the right answer. Anyone got the same answer? Anyone else? Okay, fairly easy, right? Fairly simple, just simple recursion. Great. All right, I'll see you on YouTube. All right, you guys nailed it. Great. If I were to do it, I would just do one more, P3, which is twice the population on the previous day, and then you express that in terms of P0. And in general, after t days have passed, you get 2 to the power t times your initial population. Great. Let's generalize this a little bit. This is very specific to a unicellular organism that divides in 2 every day. Okay, so hence you get the number 2. But what if it doesn't divide by 2? What if it's like, every month they, I don't know, get married and they make like 3 babies, or like, you have 1.5 baby per day, something like that. Just this number could be different. So let's generalize this in a little bit, and say that the rate of growth could be any number R, okay? Depends on the type of population. I love lobsters. I love examples of lobsters. I had lobster once in my life, but I think lobsters are really kind of interesting and cool animals, but they're kind of really weird. Like imagine you have a lobster crawling in your kitchen. It looks really weird, but in the water they look so majestic and beautiful when you're looking at them. So anyway, lobsters are going to be a recurrent example in this chapter. Anyway, so let's say you have lobsters. You start with mom and dad lobster, and then they have a bunch of babies, and then those babies meet other lobsters and they have more babies. So this population starts growing, not necessarily at the rate of doubling, could be something else, right? So in general, we say that the growth rate is R to the power t times P0. This still stands, okay? This equation still stands. If they were doing, 1.5 or 1.3 of the initial population, this is the equation. Now, an even more convenient way of writing this, rather than having a power, r to the power t, we simply express this as a exponential. So we write r to the power t as simply e to the lowercase rt. It's just a simple manipulation, okay? Nothing has changed by going from this equation to this equation. And however, the meaning of this lowercase r has a different meaning in population dynamics studies. They call it the intrinsic rate of population growth. Think of this as your accrued interest rate. It's like a rate of change per unit time that changes. Think of it as an interest rate. Point is, this is an equation for population growth. What really this exercise is to get us to this equation in this simple form. Okay, I hope you agree that you can write r to the power t as e to the rt, where r is log r, right? So if you have r log r, then you get e to the log rt, it's r to the power t. Those are the same thing, okay? But that's for a general population with a growth rate of, intrinsic growth rate of r, okay? All right, great. Now, based on this equation, if you plot the population, the population value, the number of individuals in the population versus time, you're going to get 3 different trends. If r is positive, what's going to happen? You're going to keep growing indefinitely, right? Because in that case, there are more births than there are deaths, right? Because this intrinsic rate of change of the population does account also for disappearance of the population, for example, right? So if r is positive, you're going to keep growing the population, right? If r is equal to 0, nothing is going to change. Okay, if r is equal to 0, there are no more new individuals being made, or there are as many individuals being made as are taken away. Okay, so let's say, lobsters have a baby, they take the baby and eat it, for example. This is just a horrible, very, very bad example. But, let's say the number of births is equal to the number of deaths, then there's no growth in the population, and the population is at steady state. Okay, it's not growing, it's not shrinking. And if r is negative, then the population over time is gonna shrink. Okay, great. This is an equation that we can deal with. Okay, so now in practice, in reality, populations are not described by a simple example, by as simple as this. Okay, because populations are bound by available resources. So initially, like 2 lobsters come in and they start eating everything, then they have a bunch of babies and their babies start eating everything, and then they have babies, and then there's competition to resources. And the resources, because they are limited, You know, there's not enough for everyone, so some in the population might migrate or might die, okay? Or they might have less babies, okay? There are predators involved, you know, there might be disease, right? So in practice, what happens, there's a balance, there's some sort of equilibrium that takes place in a population where initially the population starts growing very quickly, starts consuming resources, and then it reaches a plateau like this, okay? So now, assume that the number at this plateau is k. That's called an equilibrium point. That's the number of population that this P0 is going to reach. Okay. Please trust me, this has to do with differential equations, not populations, but it's a great example to think of populations. Okay. So my question to you now is the following. Take this lobster population and assume that due to food restrictions, a lobster population with an intrinsic growth rate R cannot grow beyond k individuals, okay? Go ahead and write a formula for that population growth, okay? I want you to take a moment and think about writing a formula, just like you were able to write the formula P0 e to the RT, correct? Or 2 to the power t times P0. You were able to write that, so why can't you write a formula in this case? Or why can you or can't you, okay? Take a moment. And let's see what happens. Population is growing, e to the RT, and then it reaches k. But needs to reach it smoothly, right? How can you come up with a formula for that?
Could you scale it based on the distance to k from the current spot?
What
Like
do you mean?
multiply it by something or its current position minus k?
Come up with a formula. I mean, yeah, maybe. But again, I don't know what this curve is going to look like, right? It might be steeper, it might be softer, right? Smoother. And what's the guidance? You know, you want to scale it with k, okay, but what about how fast it's changing going up there? What are the control parameters? What are the dynamics that are involved?
Oh, one is T and one is R. So the rate.
The what, Sovit? What did you say? Minus t, what?
So can we say like, you know, like k is the final parameter, right? So the maximum is k. So can we write k equals k1 and k? So k1 is going to be the initial and e to the power rt, like that way?
No, that's still not going to describe it. So in other words, you want an equation where as t approaches infinity, your answer is going to be k. And I want this to be smooth, not a switch, not say, oh, after 100 days have passed, we were growing exponentially and then we go flat. That's not how populations typically behave. I mean, even with the extinction of the dinosaurs, you know, it took them about 100 million years to die off. It's not like it happened, not 100 million years, sorry, 100,000 years, 60,000 years or so to disappear. It took them longer than humans existed, Homo sapiens existed to disappear. So there's a smooth, gradual process. Okay? Any other takers?
I'll give it a shot. I think I remember from my DiffEQs class, what if you do p over dt equals your constant times your population, parentheses 1 minus population over your carrying capacity.
Okay, so yeah, you jump the gun, which is, and you use the correct terminology, carrying capacity, but before we get there, I want the formula. What you gave me is not a formula. You gave me an equation, a differential equation, not a formula for the population. The answer here is that there's no way you could just develop a formula, you know, pull it out of your bag of tricks for this. Because there's absolutely no mechanism, no rational mechanism you are using to come up with that formula. Okay. The point that I want to make is that, and you'll see this in the unfortunately we're running out of time, but you're going to see this in the next set of slides, is that this is where differential equations come in. What we're going to do next, we're going to say, okay, this population is going to be balanced by rates of change of birth and death. We know those rates. We don't know the actual values, we know the rates. And then when we balance those rates and know that the population is going to hit K after a certain, growth time, which we don't know yet, but it's going to be embedded in the equation, then we can develop an equation, a differential equation, to help us find an equation. Okay, I'm gonna revisit these slides next on Thursday, so we can refresh our memories. But the point is, there's no way you can come up with an equation just out of a bag of tricks. You need to have a guiding mechanism, and that guiding mechanism is almost always, a differential equation. And intrinsically, the differential equation uses really common sense laws like conservation. You cannot have, a population is balanced by what's coming in and what's leaving, right? And that's the net. They're not gonna show up out of nowhere, right? So there's gonna be a new birth, and there's gonna be a death, or there's gonna be incoming lobsters coming in, and all of those are balanced, and that's your differential equation. Okay, so we will see then next Thursday how a differential equation can give us a formula to develop a formula. So instead of just jumping to develop the formula, we're going to develop a recipe that helps us develop the formula. We're going to solve the differential equation to give us the formula. Okay, all right, we're running out of time, so let's just stop it here. And I am going to share, I think I was up for a tip of life hack, okay, of the day. Okay. So let me ask you this: who of you, had a headache one day, or take some medication or something, and you opened your big jar of Tylenol from Costco that has like 10,000 pills in it, and you're like, then you drop the pill on the ground, right, on the floor. You're like, I'm not gonna take this, and you throw it away in the trash. Who's done that before? Come on. Okay, Sarah, Jenna. Abby is smiling. It's like Dylan. Okay, so you've done that before. I do that all the time. Like, there's no way, and especially let's say you're in the bathroom, you're like at the airport, and oh my gosh, I need my acid reflux medication, or something, and you have like 2 pills, and you drop one of them on the floor. You're like, oh crap, what am I gonna do, right? Okay. So this, I have an answer. I have a solution to your to that. Okay, don't call it OCD or whatever. It's just I don't want to grab a pill from the ground. I don't know. I can't get over it. And this happened to me every single time. And every single time, trust me, I'm opening a jar. I have to drop a pill. It's like it's like how I was raised. I have to drop it on the ground. And so one day we were out of the country, and we typically go visit family for about a month and a half over Christmas, and I take my acid reflux medication, so I have to take 1 pill in the morning. And typically when I'm planning my travel, I have 30 days, I take 40 pills with me, or like 35 pills, just in case we overeat on Christmas, and then I have to take like an extra pill or something. And then what happened, I was opening the jar, and I put them in these little tubes that I saved from the pharmacy, and I shake, and then the whole thing comes up. Like 15 pills come out of the jar. I'm like, oh God, what is going to happen now? I cannot buy, the medication is very expensive outside the US. So I buy it here for like, $3. I probably easily pay $50 to get a replacement pack. And so at that moment, I thought, okay, I need to get over this once and for all. So I asked myself the following question. When I bought this can of pills, I don't know where it's been. For all that's known, maybe the pharmacist put it on the floor and jumped on it and then packed it in the jar, in the container, right? But I wouldn't know that. And I don't care, actually. You know, I don't think about that. I just open the jar and take the pill, right? So if there was a way that I would not know that those pills fell on the ground, then I'd be okay. So here's what I did. I grabbed all those pills, put them in the jar, and shook it. And I'm like, okay, I don't know now. I either have to throw away the whole thing, or you know what? I was bound to take it. So now every time I'm grabbing a Tylenol or an Advil and I drop it on the ground, just grab it, put it in the can, and shake it. I'm like, okay, there's no way I know where that pill is. So, and you know what? I've never been sick because of taking a pill that had like a bacteria or something in it. It's completely irrational, right? Not to grab that pill unless it fell in, like, you know, horse excrement. But then in that case, don't put it back on the can. But anyway, I hope this helps. All right.
That's a wonderful self-hack too. A good one.
Yeah, I don't know if I swear I didn't read it anywhere. I came up with that independently, but I'm pretty sure someone has thought of that before. So, all right, thank you everyone. I have office hours from 3:30 today. If you wanna jump in and talk about anything, all right? I'll see you later.
Thank you, Dr. Saad.
Thank you. Bye bye.